generalized Vilenkin groups. First, I will say that most participants work in differential equation and something close. No, my topic is not close to this. It is from Walsh analysis. I will start with remind the definition of classical Vilenkin group. What is this classical Vilenkin group? It is associated with a positive integer p, and it consists of sequences where xj components are from this set 0, 1, etc. p minus 1, and there are at most a finite number of negative j such that xj is non-zero. So we start from some negative j and go to plus infinity, such sequences, and there is operation or plus, so-called plus, defined as coordinate wise addition modular p. This is topology. There is topology on V, topological group. It is introduced via the complete system of neighborhoods. These ones. Okay. So we see this is denoted by ZP, this set from 0 to p minus 1, and what is addition modulo p? 1 plus 1, 2, 2 plus 1, 3, etc. By minus 1 plus 1 is p or 0. So this is a cyclic group. So we can say that classical Vilenkin group is associated with the cyclic group of order p, and our goal was to extend this notion, replacing cyclic group with an arbitrary finite abelian group G. First, I will give a definition, but not for arbitrary G. For the case where group G is a group of digits for some matrix M. This I will explain. This actively used in wavelet theory, digits of matrix, but I will explain what is this first. Gotic MD denote the class of dilation matrices of order D. These are square matrices such that all their eigenvalues are bigger than 1 in absolute value. And we will denote this is M matrix, small m is absolute value of its determinant. It's clear that it is bigger than bigger or equal than 2, and M star will be used as a transport matrix to M. And what is it? Set of digits. D of M is set of digits. We say that integers L and K in ZD, in Euclidean space, are congruent modular M, and write in this way, if difference is equal to ms, where s is integer. So as ZD is split onto cosets corresponding to this relation, congruence relation, and we choose arbitrary representatives from each coset, and this is just set of digits. There are different sets of digits. D of M set of digits, and no, here what I said, as I is not equivalent to Sj from different cosets. And D star will be a set of digits with respect to matrix M star. So we have we can give a definition of the corresponding group, generalized group, but not to arbitrary, but to group that is set of digits of some matrix. What is this? It consists of the sequences x, xj, where xj are digits of matrix M, where set of digits is fixed, is chosen, and xj are non-zero only for finite number of negative j. Similar to classical Vilenkin groups. Next, we equip V with the operation. This operation, so-called plus, is coordinate-wise addition modular M. I remind that in the classical case, modular P, one-dimensional, and here a modular matrix M. And since the set equipped with this addition is well known, a finite abelian group, we denote it by G, and hence, topology, we need topological. A topology on V is introduced with a complex set of the following neighborhoods. Here they are, and so we have a topological group P that will be called generalized Vilenkin group associated with a matrix M. With a matrix M or with the corresponding group, but not for all group. Then note from general theory of groups, of topological groups, it's not difficult to see that V is a local compact abelian group. It follows from some Tikhonov theorem. It doesn't matter. It is known. It is known that there is a unique normalized Haar measure nu on such a group. This measure is full and invariant with respect to group operation. So we have this for any measurable set S. And after that, of course, we have the Lebesgue integral with respect to this measure. Similarly, nu star is a Haar measure on the space V star. And I gave the definition, but not for arbitrary G. First, I studied some concrete so-called quincunx group. It is the group of fourth order, and by direct computation proved something at present in our seminar. Unfortunately, my co-author, Alexander Vodolazov, who originally was algebraist, the first problem was if we have set of digits for matrix M, but if we have an arbitrary G, what is this group is a set of digits for some M? This was question, and my co-author understood that it's possible from algebra, from famous algebraic theorem, to prove this, not difficult. So the following theorem for a finite abelian group G of order M, there exists a matrix M, dilation matrix, such that the absolute value of its determinant is just equal to M, and this group is the group of digits is isomorphic to G. How it was proved? It was based on the following fundamental theorem from algebra. This theorem states every finite abelian group of order M is isomorphic to a finite direct sum of primary cycle groups. This one. And next he used another fundamental algebraic theorem everybody studied during student. Sorry, I want, sorry for one participant who do not understand Russian, because I want to remind it in Russian. It sounds like a poem. Гомоморфный образ группы изоморфен фактор группе по ядру гомоморфизма. И знаменитая эта формулировка, I will say you later. I don't know, in English not so beautiful. Знаменитая эта формулировка тем, что в ней единственное человеческое слово по ядру гомоморфизма, остальные все термины. Okay, so it was not so difficult, and for every M, such a group, such a matrix is appropriate. Such a matrix is appropriate. Next question, is it unique appropriate matrix? The answer no. For example, we consider this group one-dimensional. This is cyclic group Z6. Of course, one-dimensional M is 6, but it's possible to take this one or this one of order 2. Also, it's possible to take matrix of 3 times 3. All they are appropriate. Due to this theorem, we can define generalized Vilenkin group associated with a finite abelian group as a generalized Vilenkin group associated with a matrix M whose set of digits is isomorphic to J. We know now that always it is possible in different ways. Next, it appeared an unexpected thing. I remind what is local field of positive characteristic. Today, this is actively enough studied. What is this? First, let P is a prime number and Q is the power of P. Then it is known, algebra again, that the field of there is a unique up to isomorphism field of consisting of Q elements. Denote it but GFQ, and definition: a local field of positive characteristic is the set of formal Laurent series. It depends on Q. This is formal Laurent series, and coefficients AJ are just from this field JF. Next, this is a field. In a natural way, two operations, addition and multiplication, are introduced, and also norm is introduced. The norm, it is equipped with the following norm: Q minus 1, the minus L, where L is the smallest number for which AK is non-zero, smallest left. And there are a number, often some papers appear, in particular, Beher and Jahan recently published even a paper, wavelet analysis on local field or positive characteristic. Really, and wavelets is my interest, just in particular for new generalized Vilenkin group and everywhere. But it is said wavelet analysis. Really, there is some construction are described, but actually no concrete example. It is not so easy to work in the fields of positive characteristic. And now it turned out that there is the following connection with our generalized Vilenkin groups. Namely, we consider the field associated with Q, and this is a field. So in field there are two groups with respect to addition and with respect to multiplication. If G is a group consisting of Q elements, then the additive group of a field of positive characteristics, this one, just with Q, just f of Q, is isomorphic to our generalized Valentin group. So, for any additive group of a field of positive characteristic, any field is connected with our generalized Valentin group. But what about inverse? Inverse is not correct. There is a following example. If G is such a group, this is fine abelian group, but for this group there is no field of positive characteristic for which this is a group. This group is isomorphic to the corresponding additive group. So the number of generalized is wider than the number of the collection of generalized Valentin group is wider than collection of field positive characteristic. But why this is good? The notion is very new. Only about 1 month ago it appeared. So what we can take from it for this, it's possible. I will try to explain that. Nevertheless, we can take it. Okay. What first? First, we have a group. So for each group there is a dual group. This is group consisting of characters. I remind what is a character for group. This is mapping homomorphism from this group to the unit circle in a complex plane with multiplication. Operation is multiplication. And we need, I want to explain characters. Let us fix omega and define such a function of x from our generalized Valentin group V, and this formula. I will say that for classical Valentin groups, here the number, and this is just the same formula with the matrix. And omega consists coordinates of components of omega are digits of the matrix M star, and Vj are non-zero only finite number of negative number. This means that omega belongs to Vj, generalized Valentin group for matrix M star, V star. If we see to this formula, it is easy to see this. Hence, this is a corrector. And next theorem, for every continuous character on generalized group V, of V, there exists a unique omega from V star such that this character is just. So this formula gives all really gives all characters, and for standard for classical Valentin groups the same, but there are no M star, so classical Valentin group is self-dual. And here dual group is V star. But they are isomorphic as algebraic structures, but they are topological group. Let us show that these groups, V star and group of characters of group V, are isomorphic, also isomorphic as topological groups. What is it? What is topology in the group of characters? For this, we need definition of annihilators of S. S is a subset of V, and annihilator is such a set of characters for which we have this equality. And next, I remind that these sets define the topology of V, and topology of the group of characters of V is defined just by this. Next, look here, we have a trivial equality. Then we write UL annihilator of UL is this, that can be, due to this, rewritten like this. So this is just U star minus L. This means that we have isomorphism of the topological group of characters and V sub J. Next, so we have a topological group, so hence some elements of harmonic analysis are known. Let us take well-known notions and facts and statements. First of all, Fourier transform on such a group is introduced in this way. This is for any topological group here, just our characters, and X ascends to L2 in a standard way. This is for L1 and to L2 in a standard way. Then, of course, we have Planck-Sherrin formula and formula for inverse Fourier transform. And next, but I need something more to work with wavelets and something more. And I want to, how this is not started to study. Nevertheless, there is something where it's possible to take some more results on harmonic analysis and wavelet theory. This is because recently we jointly with Yuri Farkov studied so-called space of M-positive vectors developed. Just from these spaces we will take some results. What is it, space of M-positive vectors? I will next page it will be given the definition, but first of all let us consider what is for D equal to 1. This is half line. This is half line. 0, 1, 2, 3, and for example, we write in usual, for example, this is maybe associated with arbitrary p. For example, p is equal to 10. So this point is written in this way, and we see that this is very close to Vilenkin group. Vilenkin group, classical Vilenkin group may be taken for p equal to 10. And there is only one difference. Point 1 may be written 1, 0, 0, 0, or 1 is equal 0, 9, 9, etc. And this is just difference between half-line and classical Vilentin group. Something should be, this should be deleted. This is the one in the one-dimensional case, and similar construction works for multidimensional. First, let us look, then we will, here we deal with P, one-dimensional, and next we will deal with matrices. For example, this is a matrix which is called Quincke's matrix. So beautiful picture, dragon. Dragon is an analog of the interval 0, 1. 0, 1. It looks for this set of digits, for this set of digits, another dragon. Now, definition. First, we define X plus the set of vectors in the space Rd represented in the form. It is well known for if M is dilation matrix, then this is convergent series. But in difference with one-dimensional case, in the multidimensional case, it may happen that some points, there exist some points x tilde for which infinite representation is not unique. We delete all such points from one, and after that, so we take x plus minus such points where which has at most more than one representation, delete them, and then return points that have a finite representation. And such a space is called M positive vectors associated with the matrix M and a set of its digits. Very close to our generalized Vilentin groups. Very close. Let us look. This is our generalized Vilentin group. If E is a set, we can associate to such a set the corresponding set E tilde consisting of X tilde such that that corresponding to X belong to E. In particular, analog of the one, the unit interval 0, 1 is this one, U. And this is in the corresponding U tilde in the Euclidean space, bounded. It is known, such sets were studied by many authors. It is known that this is bounded Lebesgue measurable set. Its measure is an integer number depending on the choice of digits. For different set of digits, it may be different. And what about Vilentin group? Here we have normalized Haar measure. Let us normalize like this. Next, let us introduce the dilation operator. M, beautiful. M, such a big M, calligraphic, I like to say, beautiful M. If we have X from Vilentin group, then Mx is the element with shifted. So it corresponds, if we return into Y tilde, that is in, this is not group, but this is in Euclidean space. We see that this corresponds to multiplying by matrix M, and there holds this one. Okay. I thought, okay, I will finish, sorry. Okay, then we organize one-to-one pointwise correspondence because this, and we can take this is explanation, and we can take it is clear that all integrals in x tilde will be the same as integrals in our Vilentin group, but here measure Haar measure nu, and here usual measure mu, and we can just copy some result. For example, what is this? This is change of variable. We can change variables in Euclidean space with respect to measure. And here it is not clear, but everything may be written. And also we take some other, and we have wonderful spaces such that the function f itself and its Fourier transform f is also compactly supported because of this. We have such a space, the same as Vilentin groups, and some other harmonic analysis results can be taken. And after that, it's possible to develop and to take to steal from from classical wavelets and from Z M positive vectors, everything which we know on wavelets we can take. Here I presented only Haar basis. Sorry, I thought you have more 5 minutes.
Thank you very much for your nice talk. Let's applaud the speaker. And now we have